Oh, my esteemed viewers, in this tutorial, the TCP and its reliability services are clearly explained. TCP is a predominant protocol as it provides certain connection-oriented service. Some of the top-notch functions provided by TCP would include reliability related services, and it is very important to note that the reliability related services comes like a package. It includes connection establishment by three-way handshaking, ordering the segments in a proper order, that is, the order in which the packets are sent is the order in which the packets are received. Okay, ensuring no data loss and ensuring no error, and the intended receiver will only receive the packet. The second important functionality of TCP is controlling the flow control, and the other one is congestion control. In this tutorial we discuss deeply or in a greater extent how exactly TCP implements all its reliability services over the distributed application that it is enabling to the other end. TCP's responsibility is very huge, as a matter of fact, because the underlying layer from which it receives the services happens to be totally unreliable. Therefore, TCP has to safeguard its promise of providing reliability services because it is being founded on network layer, right? Therefore, we will discuss in threadbare how the reliability principles are mounted on TCP. In fact, it's an evolution, to say the least, because it was augmented or mounted on TCP. The reliability principles or reliability issues were mounted on TCP incrementally. It might have taken quite a few number of years before we saw the current TCP with its full-fledged reliability promises and implementations. And to say so, the development consisted of 5 versions of TCP as far as reliability issues are concerned. It is called as reliable data transfer protocol. The reliability component of TCP can be considered to be a corollary protocol of TCP with naming reliable data transfer. So it came in 5 versions: RDT 1.0, RDT 2.0, RDT 2.1, RDT 2.2 and RDT 3. And we will just go one by one discussing how exactly all the reliability issues were mounted as the time went by. Here in RDT 1.0, there were no channel issues. Relatively, channels were free. There were very less number of contenders, that means less number of internet users. Therefore, channels were found to be very free. Okay, and the sender would create a packet containing the data and sends the packet into the channel. On the receiving side, RDT receives a packet from the underlying channel, removes the data from the packet, and passes the data up to the upper layer. In this simple protocol, there is no difference between a unit of data and a packet, because there were very few control information, or control information is said to be nil. Also, all packet flow is from sender to receiver with a perfectly reliable channel. There was no need for the receiver side to provide any feedback to the sender, since nothing went wrong. Thus, there is no need for the receiver to ask the sender to slow down. So that was a win-win situation both for the sender as well as the receiver in the beginning days of evolution of TCP as far as reliability issues are concerned. Then came RDT 2.0. The channels showed some kind of creation of errors, and it presented a more realistic model of the underlying channel where the bits in the packets went corrupted. And this initiated error detection mechanism. Okay? A mechanism that was needed to allow the receiver to detect when bit errors have occurred. I think my respected viewers may recall from the previous section that UDP uses the internet checksum field for exactly doing this purpose. Internet checksum is meant for detecting the errors. The concept of positive acknowledgements and negative acknowledgements were introduced, and this will authenticate really the packets that were sent by the sender were received. And if it is received in correctly without any errors, the receiver would send positive acknowledgement, simply called as ACK. Otherwise, the receiver would send negative acknowledgement. And reliable data transfer protocols based on such retransmissions are known as automatic repeat request protocols. That is, if the sender receives NAK, that is negative acknowledgement, the sender would retransmit the packet again. Therefore, RDT2 and thereafter the protocols were called as automatic repeat request protocols, and succinctly ARQ protocols. Then it was the chance for RDT 2.1. Protocol RDT 2 may look as if it worked, but unfortunately it suffered a fatal flaw because both ACK and NAK also went corrupted. This is a colossal flaw, because if an ACK is coming during its backward journey towards the sender, and if ACK becomes NAK, it would necessitate the sender to retransmit the packet which was sent earlier unnecessarily. On the other hand, if the sender receives NAK, if the sender had to receive NAK, and if it becomes ACK along the way, then it is another disaster, because the sender would always assume that the packet that was sent was exactly correct and it went without any corruption. Therefore, in order to mitigate this, checksum bits were added to both ACK as well as NAK packets. Packets were placed with sequence numbers, just by 2 bits, 1 and 0. This was adopted using what is called as modulo division arithmetic, because 1 mod 2 is 1 and 0 mod 2 is 1, 0 and 2 mod 2 is 0. So therefore 1 and 0 can be cyclically generated in this RDT 2.1, and there were only 2 sequence numbers. The mechanism went something like this. A packet 1 is left and ACK would come if it went correctly and if there were no errors noticed. If packet 1 goes and if it gets corrupted in the midway, then the receiver would send NAK for packet 1. This is because the protocol state must now reflect whether the packet currently being sent or expected at the receiver should have a sequence number of 0 and 1. The packets were sent in an orderly fashion. Protocol RDT 2.1 uses both positive and negative acknowledgements from the receiver to the sender. When an out of order packet is received, the receiver sends a positive acknowledgement for the packet it has received previously. When a corrupted packet is received, the receiver sends a negative acknowledgement in case of RDT 2.1. In RDT 2.1, both ACK as well as NAK was operative, but RDT 2.2 comes with a slighter correction, that is in RDT 2.2 the concept of NAK was removed, and anyway the ACK took the responsibility of even acknowledging or negatively acknowledging a packet which was received by the receiver in the corrupted way. So RDT 2.2 avoided NAK. Instead of sending NAK for incorrectly received packet, receiver would send ACK for correctly received previous packet. That means if 1 goes correctly, ACK for 1 would be sent, and if 0 goes incorrectly with errors, then the receiver would send ACK for 1. So upon receiving duplicate ACKs, the sender will be able to know that the receiver did not correctly receive the packet following the packet that is being acknowledged twice. So this is a remarkable improvement as far as removal of NAK is concerned, because earlier in RDT 2.1 the channel was filled with huge number of ACK packets and NAK packets. There was a big confusion as far as orderly sending of the packet is concerned. Therefore, one subtle change between RDT 2.1 and RDT 2.2 is that the receiver also included the sequence number of the packet being acknowledged by an ACK message. This is done by including ACK, 0 or ACK, 1. Anyway, RDT 3 was the final version, and it is a reliable data transfer over a lossy channel, of course. As the time went by, it was noticed that an acknowledgement arriving very lately, or the packet being lost in its midway journey. This is called as a lossy channel, okay, along with bit errors. Suppose now that in addition to corrupting bits, the underlying channel can lose packets as well, a not uncommon event in today's computer networks. Okay, packets will be lost, particularly when they wait in a queue before output ports of a router. The burden of detecting and recovering from the lost packets fell on the sender. The sender transmits a data packet, and either that packet or the receiver's ACK of that packet gets lost. In either case, no reply is forthcoming at the sender from the receiver. Yeah, if the packet is lost in between, there is no question of expecting the acknowledgement, and if the acknowledgement is lost in between, acknowledgement will never be coming. Therefore, the sender will be kept in waiting. If the sender is willing to wait long enough so that it is certain that the packet has been lost, it can simply retransmit the data packet. I think all of us should be convinced ourselves that this protocol does indeed work. In order to mitigate this kind of a problem, there used to be long waits. How long a sender can wait? Therefore, there was a concept of timeout mechanism that was introduced. The sender must at least clearly wait, at least as long as a round trip delay. A round trip delay, as my respected viewers can recall, round trip delay would involve 2 end-to-end delay. Okay, going an onward journey of a packet from sender to the receiver, and a backward journey of the acknowledgement from receiver to sender. Okay, at least this much of time is to be it should be the waiting period. And of course, there are several mechanisms to compute the time delay or the timeout period. Anyway, at the sending end, implementing a time-based retransmission mechanism requires a countdown timer that can interrupt the sender after a given amount of time that has expired. The sender will thus need to be able to 1. Start the timer each time a packet leaves, is sent, or a packet is retransmitted. 2. Respond to the timer interrupt, taking appropriate actions. 3. Stop the timer. Okay, there are typical scenarios as far as RDT 3.0 is concerned. If no loss happens, this is the thing. Packet 0 leaves, packet 0 is received, and acknowledgement 0 is sent back. Acknowledgement 0 is received, packet 1 is sent, ACK 1 is received, ACK for 1 is received, and so on and so forth. And the second situation is the packet is lost in between. So packet 0 leaves, it reaches, acknowledgement 0 arrives. Packet 1 starts its journey, somewhere it is lost in between. And since it has not reached the receiver end, after a certain amount of time, packet 1 timeouts. Then the sender will once again retransmit packet 1, and ACK1 is available. It goes something like that. And the third situation is ACK is being lost. So packet 0 leaves, ACK0 appears, packet 1 leaves, and it reaches the receiver, and ACK1 arrives back. ACK1 arrives back, and in between it gets lost. Therefore, packet 1 goes out of time, or time period elapses as far as packet 1 is concerned. Then once again packet 1 is sent. The fourth situation is premature timeout. Let us see as to what it is. Packet 0 is sent, packet 0 is received, ACK0 is sent, packet 1 is sent, and acknowledgement 1 for the packet arrives, but anyway it arrives very lately. Okay, by the time the timer goes out or timeout happens for the packet 1, once again packet 1 is left. Receive packet 1, and the receiver will be able to identify the duplicacy of this packet, and it will send acknowledgement 1. Anyway, of course, this is the real mechanism that happened. Anyway, RDT 3.0 included all the reliability issues, but alas, it is a ARQ protocol, automatic repeat request protocol. A data packet has to leave, it is to be received by this receiver, and once again acknowledgement has to come. Therefore, there is a colossal bandwidth wastage because of this wait period. Therefore, there was a further improvement, and these RDT protocols were turned to be pipelined RDT protocol, and we can examine the bandwidth wastage as to how the bandwidth gets wasted due to ARQ protocol. The time needed, let us assume that the time needed to actually transmit the packet of length 8000 bits into 1 Gbps link is, it is a transmission delay typically. So transmission delay is given by 8000 bits divided by 10 to the power of 9, because it is 1 Gbps. Of course, we should have multiplied here 10 to the that is 2 to the power of 30, but anyway, since we are dividing, we are multiplying the numerator and as well as the denominator by 2 to the power of 9, 10 to the power of 9, in both the cases are 10 to the power of 6. It doesn't induce much of the error, and of course the computation of the delay happens to be little approximate. Let us assume that 1 RTT equal to 30 milliseconds. Okay, let us assume in this particular case the RTT is 30 milliseconds for a packet to reappear in the form of a acknowledgement, let us say. Therefore, channel utility is given by the formula L by R, that is transmission delay divided by RTT plus L by R. So transmission delay is found to be 0.008008 seconds, because it appeared to be 8 microseconds. Anyway, in the previous calculation, 8 microseconds divided by 10,000 will give us 8 seconds. 0.008 seconds, and 1 RTT we have assumed to be 30 milliseconds. It is 30 plus 0.008. So 30 milliseconds. This is 0.008 milliseconds, and this is 30.008 milliseconds. Therefore, the channel utility is 0.00027. The meaning is the sender was busy only 2.700, that is 2.7 divided by 100, will become 0.0027 of 1% of the time. That is, once again it is divided by 100, it gives us this particular thing. So this is another kind of expression. Okay, here the statement here is another kind of expression for this colossal wastage of bandwidth. That means for the entire period of only this much, the biggest capacity of the channel amounting to 1 gigabyte has been used only to send only one packet. Okay, because the sender was busy or the channel was busy. We can say like that also. The channel was busy only for 2.7 hundredths, that is 2.7 divided by 100 of 1%, that is 1 into 1 over 100. So that becomes this particular thing. Okay, therefore we found, I think it is becoming increasingly clear for us, though all the reliability issues were implemented until the point of RDT 3.0, it is a major flaw because this protocol is automatic request repeat protocol, and there is a lot of waiting period and a colossal bandwidth wastage. Therefore the reliability issues comes in a different form. The solution to this particular performance problem is simple. Rather than operate in a stop and wait manner or ARQ manner, the sender is allowed to send multiple packets without waiting for the acknowledgements. So the channel turned into something like this. Before ACK for this arrives, there are several packets that must have left the sender. Therefore, the pipeline, that the channel is always filled with data packets in the forward journey and ACK packets in the backward journey. Therefore, the complete bandwidth is utilized. The figure above, that is this figure just now explained, shows that if the sender is allowed to send as much packets as it can before having to wait for acknowledgements, by doing so, the utilization of the sender is tripled, or it becomes multiple times. Okay, utility becomes increased. Since the many in-transit sender to receiver packets can be visualized as filling a pipeline, this technique is known as pipelining. So with this, there are two basic approaches toward pipeline RDT protocols. They are named as go back and selective repeat. So my dear viewers, in the tutorial 3 we discuss go back and selective repeat. Until then, bye, and if you liked this video, kindly subscribe to my channel.